Alright, so today I will be reading this material about Python's asyncio. Actually, I read halfway through, but I'm going to start over for the sake of the video. Um, I hope it will be interesting topic for you guys and just doing for myself satisfaction though. Alright, let's just dive right in. Sorry, I stuttered. Hold on, I have a message from someone. Okay. Alright, so Python's asyncio, a hands-on walkthrough. We got plenty of contents right here. Let me go from the top. Okay, I think this is just an introduction that we can skip. Okay, so first look at asyncio. Let me make it bigger for you guys. I think it's big enough. Alright. First look at asyncio. Before exploring asyncio, it's worth taking a moment to compare asyncio with other concurrency models to see how it fits into Python's broader, sometimes dizzying landscape. There are some essential concepts to start with. Parallelism. Parallelism consists of executing multiple operations at a time. Multiprocessing. It means of achieving parallelism that entails spreading tasks over a computer-centered processing unit cores. Multiprocessing is well suited for CPU-bound tasks such as tightly bound for loops and mathematical computations. And I'm not sure how to translate this one, so let me check. Entails. Okay, I can add that to my vocabulary. There we go. Entail. Oh, I already marked it, and I completely forgot about that up until now. Concurrency is a slightly broader term than parallelism, suggesting that multiple tasks have the ability to run in an overlapping manner. Concurrency doesn't necessarily imply parallelism. Okay, so threading is a concurrent execution model in which multiple threads take turns executing tasks. A single process can contain multiple threads. Python's relationship with threading is complicated due to the GIL, but that's beyond the scope of this tutorial. Threading is good for IO-bound tasks. An IO-bound job is dominated by a lot of waiting on input-output to complete, while a CPU-bound task is characterized by the computer's cores continually working hard from start to finish. The Python standard library has offered long-standing support for these models through its multiprocessing, concurrent.features, futures, and threading packages. Now it's time to add new member to the mix. In recent years, a separate model has been more comprehensively built into CPython, asynchronous I/O, commonly called async I/O. This model is enabled through the standard libraries, async I/O package, and the async and await keywords. The async I/O package is built by the Python documentation as a library to write concurrent code. Is built. I don't know how to translate that in terms of this context. The translation is not that good here. Let me open up Claude. Wow, okay. Anyways, however, async I/O isn't threading or multiprocessing. It's not built on top of either of these. Async I/O is a single-threaded, single-process technique that uses cooperating multitasking. Async I/O gives a feeling of concurrency despite using a single thread in a single process. Coroutines, or for short, are a central feature of async I/O and can be scheduled concurrently, but they're not inherently concurrent. Okay. To reiterate, async I/O is a model of concurrent programming, but it's not parallelism. It's more closely aligned with the threading than with multiprocessing. But it's different from both and is a standalone member of the concurrency ecosystem. That leaves one more term. What does it mean for something to be asynchronous? This isn't a rigorous definition, but for the purposes of this tutorial, you can think of two key properties. Asynchronous routines can pause their execution while waiting for the result and allow other routines to run in the meantime. Asynchronous code facilitates the concurrent execution of tasks by coordinating asynchronous routines. Here's a diagram that pulls it all together. The white terms represent concepts and the green terms represent the ways they are implemented. Let me put up my desk. I'll stand up a little bit. For a thorough exploration of threading versus multiprocessing versus async I/O, pause here and check out the Speed Up Your Python Program with Concurrency tutorial. For now, you focus on async I/O. Okay. Let me pause here. I'm gonna grab some water. Okay, I'm back. So here I would like to mention like high level difference between multiprocessing and there's a by the way, it doesn't show here, it doesn't show up here, but there is another concept of uh, multi-threading, yeah, or maybe mentions here threading, yeah, but there is a concept of multiprocessing, multi-threading, and the major difference is that multiprocessing, it has their own um, let's say memory space, whereas multi-threading, they have a part where they share memory space among different threads. Um, so that's one thing that you might want to know about the difference between multiprocessing and multi-threading, and I'm not going to cover deep in detail about those differences. But major difference is that, like, key takeaway, when you're asked what's the difference between multiprocessing and multi-threading, you might want to explain what I just said first. So let's go to the next chapter. Async I/O explained. Async I/O may seem counterintuitive and paradoxical at first. How does something that facilitates concurrent code uses single thread in a single CPU core? Miguel Greenberg's PyCon talk explains everything quite beautifully. Chess master Judith Polgar hosts a chess exhibition in which she plays multiple amateur players. She has two ways of conducting the exhibition, synchronously and asynchronously. Assumptions: 24 opponents. Judith makes each chess move in 5 seconds. Opponents take 55 seconds to make a move. Games average 30 pair moves. 60 moves total. Okay. Synchronous version. Judith plays one game at a time, never two at the same time. Until the game is complete, each game takes 55 plus 5 times 30, that is 1800 seconds and 30 minutes. No, I mean 1800 seconds or 30 minutes. The entire exhibition takes up to 24 times 30, that'll be 12 hours. Asynchronous version, Judith moves from table to table, making one move at each table. She leaves the table and lets the opponent make their next decision during the wait time. One move on all 24 games takes Judith 24 times 5. That'll be 2 minutes, and the entire exhibition will be just 1 hour. Okay. There's only one Judith Polgar who makes only one move at a time. Playing asynchronously cuts the exhibition time down from 12 hours to 1 hour. Async IO applies this principle to programming. Async IO, in Async IO, a program event loop, more on that later, runs multiple tasks, allowing each to take turns running at the potential optimal, no, no, running at the optimal time. Async IO takes long-running functions like a complete chess game, in an example above, that would block a program's execution. It, manage, it manages them in a way so other functions can run during that downtime. In the chess example, Judith Pulgar plays with other participant while the previous ones makes their moves. Okay. Async IO isn't simple. Building durable multi-threaded code can be challenging and prone to errors. Async IO avoids some of the potential speed bumps you might encounter with multi-threaded design. However, that's not to say that asynchronous programming is a simple task in Python. Be aware that async programming can be tricky when you venture a bit below the surface level. Python's async model is built around concepts such as callbacks, coroutines, events, transports, protocols, and futures. And even just the terminology can be intimidating. That said, the ecosystem around async programming in Python has improved significantly. This async IO package has matured and now provides a stable API. Additionally, its documentation has received considerable overhaul, and some high-quality resources on the subject have also merged. Multi-threading, and um, multi-threading and async programming is kind of similar for certain people in a sense that whereas multiprocessing is meant for CPU, I mean it's best for CPU bound task, whereas these two, multi-threading and asynchronous programming, is best suited for IO bound tasks. But there's a major difference between multi-threading and asynchronous programming that I understand is that asynchronous programming you will be um, you will declare when you want to pass the execution to other programs. Um, Whereas multi-threading, it will be done through context switching. Of course, context switch happens all the time, and that even happens in asynchronous programs as well. But in asynchronous program, you will be controlling to somewhat extent. I mean, you will have a apart from automatic context switch, you're going to have a control on when to notify that other program can be executed. All right, let's move on. Async IO in Python with async IO. Now that you have some background on async IO as a current concurrency model, it's time to explore Python's implementation. Python's async IO package and its two related keywords, async and await, serve different purposes but come together to help you declare, build, execute, and manage asynchronous code. Coroutines and coroutine functions. At the heart of async IO is the concept of a coroutine, which is an object that can suspend its execution resume it later. In the meantime, it can pass the control to an event loop, which can execute another coroutine. Coroutine objects result from calling a coroutine function, also known as an asynchronous function. You define one with the async def construct. Before writing your first piece of asynchronous code, consider the following example that runs synchronously. So let me read. So it starts. Okay, so it's just for performance measuring purpose, and what's called inside main is a count being looped. So in count, you will print one, and you're going to wait for 1 second or 1 millisecond. I'm not sure. But anyways, you're going to wait for a certain period of time, and then you print out 2, and then you sleep again, same amount, and that'll be done for 3 times. The count function. Okay, so this is just an explanation about the code, which I did already, so I'm going to skip it. When you run this script, you will get the following output: 1 2 1 2 1 2. Yeah, that makes sense. And the script prints 1 and 2 alternatively, taking a second between each printing operation. So it's a second, it's not millisecond. Good. In total, it takes a bit more than 6 seconds to run. Reason for that is probably call stack. Yeah, think so. Because for loop creates a call stack. If you update this script to use Python's async IO model, then it would look something like the following. So now notice that we are using different approach for halting the program. Before it was using the time library, but now we're using async IO library, and it's calling the sleep method. And yeah, main function's a bit different as well. I'm going to just read the description. Now you use the async keyword to turn count into a coroutine function that prints 1, waits for a second, then prints 2, and waits another second. You can use the await keyword to await the execution of async io.sleep. This gives the control back to the program's event loop, saying, I will sleep for 1 second, go ahead and run something else in the meantime. The main function is another coroutine function that uses async IO gather to run 3 instances of count concurrently. You use this async io.run function to launch event loop and execute main. Compare the performance of this version. So this will be done alternatively. So first count will be executed, prints 1, and here when you execute it, it waits for 1 second, but at the same time it will let the coroutine is it coroutine? Hold on. Event loop. It lets the event loop know that something else could be executed in the meantime. And because of that reason, the second count will be called. So print 1, and also does the same thing here. So it will go to the third count and prints 1. So printing 1 is done almost at the same time. Waits for 1 second, and 2 is printed also almost at the same time. And that's the result of the execution of the code. Thanks to the async IO approach, the total execution time is just over 2 seconds instead of 6, demonstrating the efficiency of async IO for IO bound tasks. While using time sleep and async IO sleep may seem banal, what does that mean? Something that means like stupid or no? Hey, well, not alright. So it's like normal. They serve as stand-ins for time-intensive stand-ins. Probably it means something like example. Okay, yeah, like example or substitute. They serve as stand-ins for time-intensive processes that involve wait time. A call to time.sleep can represent a time-consuming blocking function call, while asyncio.sleep is used to stand in for a non-blocking call that also takes some time to complete. You'll see in the next section the benefit of waiting something, including asyncio.sleep, is that the surrounding function can temporarily cede control to another function that is more readily able to do something immediately. In contrast, time.sleep or any other blocking call is incompatible with asynchronous Python code because it stops everything in its tracks for the duration of the sleep time. In its tracks. Stop in its tracks. Okay, stops everything in its tracks. That's interesting. I think I saved it sometime. No, I didn't. Okay. Alright, anyways. The async and await keywords. How long have I been? Okay. At this point, a more formal definition of async, await, and the coroutine functions they help you create is in order. The async def syntax construct introduces either a coroutine function or an asynchronous generator. The async with and async for syntax constructs introduce asynchronous with statements and for loops respectively. The await keyword suspends execution of surrounding coroutine and passes control back to the event loop. To clarify the last point a bit, when the Python encounters a wait f expression in the scope of a G coroutine, await tells the event loop suspend the execution of G until the result of f is returned. In the meantime, let something else run. In code, that last bullet point looks roughly like the following. There's also a strict set of rules around when and how you can use async and await. These rules are helpful whether you're still picking up the syntax or already have exposure to using async and await. Using the async def construct, you can define a coroutine function. You may use await, return, or yield, but all of these are optional. Await, return, or both can be used in regular coroutine functions. To call coroutine function, you must either await it to get its result or run it directly in an event loop. Yield used in an async def function creates an asynchronous generator. To iterate over this generator, you can use an async for loop or comprehension. Async def may not use yield from, which will raise a syntax error. Using await recursion might take super long, and supposing async is meant for doing read and write operations to the external systems or something like that. That's why they don't like it. Maybe I'm not sure why they are not allowing it, but yeah, I imagine that if you use yield from, that's the syntax that's typically used for recursion. So yeah, if recursion occurs and then in each recursion will execute something that's extremely costly, that's not good for that's not good for everybody. So using await outside of an async def function also raises syntax error. You can only use await in the body of coroutines. Let me confirm this. Why? Async def functions cannot use yield from because they serve different purposes and have incompatible execution models. Different coroutine types, async def creates native coroutines, while yield from is for generator-based coroutines. Syntax replacement in async functions await replaces yield from for delegating to other coroutines. Execution model conflict. Async def functions use await for suspension points, while yield from is a generator delegation mechanism. Mixing them will create ambiguity about how the function should behave. Mm. Okay. Can you call? Can you do recursion using async def? No, as a generator. Okay. Here are some terse examples. Terse. That's a new word. I actually came across with it before because I marked it. Example that summarizes these rules. Okay. Finally, when you use await f, it's required that f be an object that's awaitable, which is either another coroutine or an object defining an await special method that returns an iterator. For most purposes, you should only need to worry about coroutines. Here's a more elaborate example of how async IO cuts down on wait time. Suppose you have a coroutine function called makeRandom that keeps producing random integers in the range 0 from 0 to 10 and returns when one of them exceeds the threshold. In the following example, you run this function asynchronously 3 times. To differentiate each call, you use callers. So what does it do? It will call async arrow run main. What does it do? It will call make a random 3 times by passing different parameters. Make random here. Choose colors. Delay. What is this? Delay is okay. 1, 2, 3. Okay. 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 Then random int threshold number. Okay, that's random number that's being created, and then that's a threshold. If it doesn't surpass the threshold, it will sleep. Okay. The colorized output speaks louder than a thousand words. Here's how this script is carried out. Okay. Can I pause? Let me see. Okay, hold on. Too slow. Initiating too slow. Make random. Too low. Hmm. So what happened in the first second is that it initiated these three call routines, and it luckily got into this while loop. The first one having to wait for 4 seconds, the second one having to wait for 4 seconds, the third one having to wait for 0 seconds, and that's why in the next second, what? Will be trying. Okay. So apparently, finish. Column 3. Too low. Delay. Delay is 3. Delay is 3. Okay, so 1. Okay, it executes, and then second, and The blue comes next and purple comes next. Because this one only has to wait 1 second, this one 2 seconds, this one 3 seconds. So 2 1s and two. There's 2 1s and 1 2, and right after that will be purple. Okay, I understand that. Okay, this program defines the marker random coroutine and runs it concurrently with 3 different inputs. Most programs will consist of small modular coroutines and a wrapper function that serves to chain each smaller coroutines. In main function, you will gather the 3 tasks, the 3 calls to make random function are your pool of tasks. While the random number of generation in this example is CPU bound task, its impact is negligible. The async IO.sleep simulates an IO bound task and makes the point that only IO bound or non-blocking tasks benefit from the async IO model. So yeah, never use async IO or multi-threading when your computation complexity comes, or when your execution time comes from CPU instead of IO operations. Okay, let me take a break. Alright, there we go. I think we have gone through as long as here, so we can start again from here. In a synchronous programming, an event loop is like an infinite loop that monitors coroutines, takes feedback on what's idle, and looks around for things that can be executed in the meantime. It's able to wake up an idle coroutine when whatever that coroutine is waiting for becomes available. The recommended way to start an event loop in modern Python is to use asyncio run. This function is responsible for getting the event loop running tasks until they complete and closing the loop. Can't call this function when another async event loop is running in the same code. You can also get an instance of the running loop with the get running loop function. If you need to interact with the event loop with a Python program, the above pattern is a good way to do it. The loop object supports introspection with is running and is closed. It can be useful when you want to schedule a callback by passing the loop as an argument. For example, that running get running loop raises runtime error expression if there's no running event loop. Let me try this one. Available, remember later. Okay, so Python import async IO. Runtime error. No running event loop. Good. There's no running loop. Async IO. How to start loop. Event loop. Get event loop. Okay. Get event loop. Okay. And then is running. Not running. Is complete. No. What was it? Is closed. Okay. False, false. Oh, really? Uh, hmm. What's more important is understanding what goes on beneath the surface of the event loop. Here are a few points worth stressing. Coroutines don't do much on their own until they are tied to the event loop. By default, an async event loop runs in a single thread and on a single CPU core. In most async I/O applications, there will be only one event loop, typically in the main thread. Using multiple main, using, hold on, running multiple event loops in different threads is technically possible, but not commonly needed or recommended. Event loops are pluggable. You can write your own implementation and have it run tasks just like the event loops provided in async I/O. Regarding the first point, if you have a coroutine that awaits others, then calling it in isolation has little effect. Hmm. Yeah, it doesn't execute because it doesn't await. In this example, calling main directly returns a coroutine object that you can't use in isolation. You need to use async IO run to schedule the main coroutine for execution on the event loop. Hmm. You typically wrap your main coroutine in an async IO dot run call. You can execute lower level coroutines with await. Hmm. Finally, the fact that the event loop is pluggable means that you can use any working implementation of an event loop, and that's unrelated to your structure of coroutines. The async IO package ships with two different event loop implementations. Defen- the default event loop implementation depends on your platform and Python version. For example, on Unix, the default is typically selector event loop, while Windows uses proactor event loop for better subprocess and I/O support. Third-party event loops are also available. For example, the EUV loop package provides an alternative implementation that promises to be faster than the async IO loops. The async IO REPL, okay, I have no interest in this part. It's not the essential concept. No. Async IO has its own set of possible programming patterns that allow you to write better asynchronous code. In practice, you can chain coroutines or use a queue of coroutines. You will learn how to use these two patterns in the following sections. Coroutine chaining. A key feature of coroutines is that you can chain them together. Remember, a coroutine is awaitable, so another coroutine can await it using the await keyword. This makes it easier to break your program into smaller, manageable, and reusable coroutines. The example below simulates a two-step process that fetches information about a user. The first step fetches the user information, and the second step fetches their published posts. So what they mean about chaining is, hold on, I think I'll gather. Get user with posts. User ID is given here, and in the user ID, so inside of the get user with posts, it waits for another coroutine that's called fetch user, and inside of that fetch user is calling another coroutine that's sleep. I think it's a mock for API call, and fetch posts. Yeah, after fetching the user is fetch post, which will fetch another type of data from an endpoint. That's what they mean by um, what did they say? Coroutine chaining. In this example, you define two major coroutines, fetch user and fetch post. Both simulate a network call with a random delay using asyncio sleep. A fetch user coroutine, you return a mock user dictionary, and in fetch posts, you would use that dictionary to return a list of mock posts attributed to the user at hand. Hold on. You use that dictionary to return a list of Mm, attributed. Okay. Random delays simulate real-world asynchronous behavior like network latency. The coroutine chaining happens in the get user with posts. This coroutine awaits fetch user and stores the result in the user variable. Once the user information is okay, so it's just saying what I was explaining at the first place. If you sum up the time of all operations, then this example would take around 7.6 seconds with a synchronous implementation. However, with the asynchronous implementation, it only takes 2.68 seconds. The pattern consisting of awaiting one coroutine and passing its result into the next creates a coroutine chain, where each step depends on the previous one. This example this example mimics a common async workflow where you get one piece of information and use it to get related data. Coroutine and queue integration. Asyncio package provides a few queue-like classes that are designed to be similar to classes in the queue module. In the example so far, if you haven't needed a queue structure, in the example so far, you haven't needed a queue structure. In chain.py, each task is performed by a coroutine which you chain with others to pass data from one to the next. An alternative approach is to use reducers that add items to a queue. Each reducer may add multiple items to the queue at staggered, random, and unannounced times. Then a group of consumers pulls items from the queue as they show up greedily and without waiting for any other signal. In this design, there's no chaining between producers and consumers. Consumers don't know the number of producers and vice versa. It takes an individual producer or consumer a variable amount of time to add and remove items from the queue. Hold on, let me read it again. It takes an individual producer or a consumer a variable producer or consumer a variable amount of time to add and remove items from the queue. It's kind of confusing. It takes an individual. A variable amount of time to add. Okay, okay. The queue serves as a throughput, so it's just saying this will be um, this will be a coroutine. The queue serves as a throughput that can communicate with the producers and consumers without them talking to each other directly. The queue-based version of chain.py is shown below. You are going to initialize queue, and what do? You pass in the queue to producer and consumer, and producer is going to fetch fetch user and then put the result into the queue. Average. And in the consumer part, what it does is to get an item from the queue. If user is none, then break. Why sentinel? I'm not sure why they're putting these sentinels, but is it really needed? If there's no none, there will be, because user IDs are, we have 3 user IDs, so 3 users will be put. And we get 1 out of 3. We don't check this one. Delay, sleep delay, post, in posts. Not sure why we need these sentinels, but for consumers to terminate. For consumers to terminate. Okay, so it, well, true. Get. Yeah, of course. Yeah, I get that. In this example, the producer function, okay, let me explain my understanding. So if there's no none, apparently, qget will try to get something when there's nothing. So if there's nothing, it doesn't just stop. It just try to execute uh, what's just given right there on the queue, and then execute this post request without the necessary information, and then probably will raise an error or anything like that. So you have to control this program so it eventually stops. Okay, so in this example, the producer function asynchronously fetches mock user data. Each fetched user dictionary is placed into an async IO queue object. Okay, it's just an explanation that I just did right there. Okay. Again, the code runs only blah 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 blah. Okay, let's go move on. Other async IO features. Hold on. Python's async IO features extend beyond the async def and await constructs. They include other advanced tools that makes asynchronous programming more expressive and consistent with regular Python constructs. In the following sections, you will explore powerful async features, including async loops and comprehensions, the async with statement, and exception groups. These features will help you write cleaner, more readable asynchronous code. Async iterators, loops, and comprehensions. Apart from using async and await to create coroutines, Python also provides the async for construct to iterate over an asynchronous iterator. Asynchronous iterators allows you to iterate over asynchronously generated data. While the loop runs, it gives control back to the event loop so that other async tasks can run. A natural extension of this concept is a asynchronous generator. Here's an example that generates powers of 2 and uses them in a loop and comprehension. Main function powers of 2. What it does is to take exponent. Well, exponent stops, so stop will be 5. Yield 2 to the power of exponent. So the initial value is 0. So 1 is passed. And then next one exponent is incremented, and it slips for a bit. and in the next iteration, 2 will be passed down to here, as I. So 0, 2, 4, 8, 16 is passed. 0, 2, 4, 8, 16. Yeah, it's passed. Yeah, that's what we get right here. There's a crucial distinction between synchronous and asynchronous generators, loops, and comprehensions. Their asynchronous counterparts don't inherently make iterations concurrent. Instead, they allow the event loop to run other tasks between iterations when you explicitly yield control by using a wait. The iteration itself is still sequential unless you introduce concurrency by using async IO gather. Using async for and async with is only required when working with asynchronous iterators or context managers where a regular for or with would raise errors. Async with statements. The with statement also has a asynchronous version. Async with. The construct is quite common in async code, as many IO bound tasks involve setup and teardown phases. For example, say you need to write a coroutine to check whether some websites are online. To do that, you can use AIO HTTP, which is a third-party library that you need to install by running Python npm install blah blah blah. Okay, here's a quick example that implements the required functionality. What it does: websites, we have a bunch of them. Gather, check URL. Okay, check URL. Async IO gather. You can pass function. Okay, you can pass the object, coroutine object. But haven't I seen gather? I think I've seen somewhere that the example code is passing the function itself, not the coroutine. Not sure where it was. Or maybe it's just here. Async IO run routine. Because routine is the result of main. So okay, that makes sense. Where was I? I was here. Okay. Okay, let's start it over. So check. What we do is to receive URL and then execute get, and initializing a sticky session with IO HTTP, and then async IO with it's a context. Okay, it's another context of a request, and then you can do something related to that request within that scope. In this example, you use AIO HTTP and async IO to perform concurrent HTTP GET requests to a list of websites. The check routine fetches and prints the website status. The async with statement ensures that both client session and the individual HTTP response are properly and asynchronously managed by opening and closing them without blocking the event loop. In this example, using async with guarantees that underlying network resources, including connections and sockets, are correctly released, even if an error occurs. Finally, main runs to check coroutines concurrently, allowing you to fetch the URLs in parallel without waiting for one to finish before starting the next. I like the way how they put it. Yeah, I don't have the ability to tell this behavior in a like in such an understandable manner. Yeah, parallel without waiting for the one to finish. Yeah, yeah, fetch something parallel without waiting for one to finish before starting the next. Yeah, that's a good take. Other async IO tools. In addition to async IO run, you've used a few other package level functions such as async IO gather and async IO get event loop. You can use async IO create task to schedule the execution of a coroutine object followed by the usual call to the async IO.run function. So what it does, async IO run, and we pass main coroutine object inside of which we create a task using this method, uh, which takes another coroutine defined in here, and return await task. Okay, so main returns await task. I don't see the point here. Can you not just remove all of it and then call coro without having to create task? This pattern includes a subtle detail you need to be aware of. If you create tasks with create tasks, but you don't await them or wrap them in gather, and your main coroutine finishes, then those manually created tasks will be cancelled and when the event loop ends. You must await all tasks you want to complete. The create task function wraps an awaitable object into a higher level task object that's scheduled to run concurrently on the event loop in the background. In contrast, awaiting a coroutine runs it immediately, pausing the execution of the caller until the awaited coroutine finishes. The gather function is meant to neatly put a collection of coroutines into a single future object. This object represents a placeholder for a result that's initially unknown but will be available at some point, typically as the result of asynchronous computations. if you await gather and specify multiple tasks or coroutines, then event loop will wait for all tasks to complete. The result of gather will be a list of results across the inputs. Hmm. I want to try something, so let me close this. Okay, so and then test.py. No. Python. This code. Okay. I need to write it. And if So this is not necessary, but you want to like this is something that you want to use you if you want to like elevate your coroutine into a higher object called task and want to do something. I'm not sure. I'm not seeing a point right here. Okay, let's move on. Let's move on for now. You probably noticed that gather waits for the entire result of the whole set of coroutines that you pass it. The order of results from gather is deterministic and corresponds to the order of avoidables originally passed to it. Alternatively, you can loop over asyncio as completed to get task as the complete. Okay, the function returns asynchronous iterator that yields tasks as they finish. Below the result of coro 321 will be available before coro 1052 is complete, which wasn't the case with the gather function. Gather function. Okay, this one. Create task, coro numbers. Okay, okay, minimum. So 2 is weighted and 1 is weighted. And result is ordered accordingly with the coroutines given. But in this example, print start tasking async as completed. Wait task. In this example, the main function uses as completed function, which yields tasks in the order they complete, not in the order that they were started. As the program loops through the tasks, it awaits them, allowing the results to be available immediately upon completion. As a result, the faster task finishes first, and its result is printed earlier, while the longer task completes and prints afterward. Hmm. It took 3 seconds. Took 2 seconds. And this took 2 seconds as well. Yeah, because we're waiting for both to end. Yeah, of course. As a result, when you need to handle tasks dynamically as they finish, which improves responsiveness in concurrent workflows. Async exception handling. Return exceptions. Where's exception? Okay, starting with Python 3.11, you can use the exception groups class to handle multiple unrelated exceptions that may occur concurrently. This is especially useful when running multiple coroutines that can raise different exceptions. Additionally, the new except asterisk syntax helps you gracefully deal with several errors at once. Here's a quick demo of how to use this class in asynchronous code. Okay, coro can raise value error, coro B can raise type error, coro C raises index error. Async gather return exceptions true. Results. If it's exception, then exception is returned. back to here, and then if exception is not a empty, rate exception group, errors exceptions. In this example, you have three coroutines that raise three different types of exceptions. In the main function, you can call the other with the coroutines as arguments. You can also set return exception argument to true, so you can grab the exceptions if they occur. To handle this exception group, you can use the following code. asyncio run asyncio.run main value error te group okay te value error type error okay. In this code, you wrap the call to asyncio.run in a try block. You can then use the except as their syntax to catch the exception separately. In this case, in each case, you print an error message to the screen. Excuse me, to the screen. Now that you've seen a healthy dose of asynchronous code, take a moment to step back and consider when asyncio is the ideal choice and how to evaluate whether it's the right fit or if another concurrency model might be better. Probably it's going to talk about CPU bound or IO bound. Yeah, let me just read it. Anyways, using async def for functions that perform blocking operations such as standard file I/O or synchronous network requests will block the entire event loop, negate the benefits of async I/O, and potentially reduce your program's efficiency. Only use async def functions for non-blocking operations. The battle between async I/O and multiprocessing isn't a real battle. You can use both models in concert if you want. In practice, multiprocessing should be the right choice if you have multiple CPU-bound tasks. The contest between async I/O and threading is more direct. Threading isn't simple, and even in cases where threading seems easy to implement, it can still lead to a hard to trace bugs due to race conditions and memory usage, among other things. Threading also tends to scale less elegantly than async I/O because threads are a system resource with a finite availability. Creating thousands of threads will fail on many machines or can slow down your code. In contrast, creating thousands of async I/O tasks is completely feasible. Async I/O shines when you have multiple I/O bound tasks that would otherwise be dominated by blocking wait time, such as network I/O, whether your program is acting as a server or the client. Serverless designs such as peer-to-peer multi-user network like a group chat, read-write operations where you want to mimic a fire and forget style approach without worrying about holding a lock on the resource. The best reason not to use async I/O is that await only supports a specific set of objects that define a particular set of methods. For example, if you want to do async read operations on a certain database management system, then you need to find a Python wrapper for DBMS that supports the async and await syntax. So the difference between threading and async I/O is that hold on, it's a scale list. So infinite availability. Creating thousands of threads will fail. Yeah, just like a C10K problem. When a program tries to create more threads than it should be, and it starts to decay. In contrast, create is completely invisible. So like you can take that threading happens in the lower level and async IO happens in the language level. That's another difference to notice. Okay, so there are a set of libraries that supports async IO, Fast API, Starlit. Didn't know this one. Sanic, Quad, Tornado, Unicorn, Hypercorn, async IO, blah 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 databases, utility libraries, IO files, IO cache, API scheduler, PyTest async IO. These libraries very much help you write performant async Python applications. Whether you're building a web server, fetching data over a network, or accessing a database, async IO tools these give you the power to handle many tasks concurrently with minimal overhead. Alright, conclusion. We came to here, to the bottom line. Alright, so you've gained a solid understanding of Python's async IO library and the async and await syntax, learning how asynchronous programming enables efficient management of multiple IO bound tasks within a single thread. Along the way, you explore the differences between concurrency, parallelism, threading, multiprocessing, and asynchronous IO. You also work through practical examples using coroutines, event loops, chaining, and queue-based concurrency. On top of that, you learn about advanced async I/O features, including async context managers, async iterators, comprehensions, and how to leverage third-party async libraries. Mastering async I/O is essential when building scalable network servers, web APIs, or applications that perform many simultaneous I/O bound operations. Okay. Frequently asked questions. Oh, that's interesting. Now that you have some experience with async IO Python, you can use these questions and answers below to check your understanding and recap what you have learned. Okay, what is async IO in Python and why should you use it? Because it enables a for concurrency that you will best benefit from executing IO bound tasks. You use async IO to write concurrent code with the async and await keywords, allowing you to efficiently manage multiple IO bound tasks in a single thread without blocking your program. That's great. Yeah, more or less the same. Let me hide this one. Is async IO better than multi-threading for IO bound tasks? Threading can cause to a system halt due to too many thread due to too many threads being in your machines. Uh, but according to the material, I think I many as like you can create as many coroutines as you want. So in that sense, async IO is better. Also, multi-threading um, can cause race conditions because it shares uh, shares the same memory space among different threads. So if that happens, it's quite difficult to debug. So yeah, that's a benefit over multi-threading for async IO, right? You typically get better performance from async IO for IO bound work because it avoids overhead and complexity of threads. This allows thousands of tasks to run concurrently without limitations of Python. This allows thousands of tasks to run concurrently without limitations of Python. Yeah. When should you use async IO in your Python Pro? When there's IO bound, when you have a task that's dominated by IO bound tasks, right? Yeah. How do you define and run coroutine with async IO? With async and await keyword. Okay, I forgot about that. Async IO run the schedule. Create task. Okay, you can define coroutine async. Yeah. This one, and to run it, you either pass it to async and run or schedule it as a task with create task. Okay. What role does the event loop play in async IO for executing coroutines? You rely on the event loop to manage the scheduling and execution of your coroutines, giving each one a chance to run whenever it awaits for or completes an IO bound operations. Okay. Okay, that's it. I hope it was fun for you guys too. I will see you soon. Bye bye.